I'm going to do that. Go ahead, Jill, sorry.
So I was going to say, Phil, that's fascinating. I wrote it down, fractotopography. But so this might be a question for much later when we get to the last part, because what I think about at the landscape scale is, you know, how do you disentangle the imprint of changing conditions through time? You know, so for example, going from somewhere where you might have a cold and dry climate to a wet and warm climate, you know, or we're you're in Jeffrey's world of the rivers, and your abrasion, your loads coming down that stream might change. The grain size distribution even that's hitting those rocks might change over time, depending upon how much precipitation you have. So that's I'm just putting that in your back pocket for later on. When I hear you say that, that's the first thing I think is, oh my God, that's amazing. And then the world is so complex. How do we even deal with it?
Dorothy, go ahead.
Yes, I think it's a follow-up to what you just said, Philip, in that the fractures I'm most interested in right now, although all are fascinating, the ones I'm interested in at the moment are in the formerly periglacial regions of North America, primarily Eastern North America, south of the repeated full glacial ice margins. And there's this belt of land that has prominent thermal contraction polygonal networks. And where there's bedrock, the thermal contraction cracks have followed pre-existing bedrock fractures. So it's, I think, going back to your point about the patterns were already there in the bedrock. Shale in particular makes excellent thermal contraction cracks.
Yeah, yeah.
It's amazing. I heard one of you mention shale yesterday, and I was intrigued by that comment that you study shale. But in the coastal plain to the east, in New Jersey, for example, these full glacial condition thermal contraction polygons are very kind of random polygons. They don't have that clear pattern. And we've actually measured the fractures. We've measured hundreds. Bob Walter, my colleague, has done this, hundreds of bedrock fractures in the same places where we've also measured the orientations of hundreds, maybe thousands of the boundaries of thermal contraction polygons. And they're completely lined up with one another, where there's shelly bedrock in particular. So there must be something about the cracking. It's reactivating during cold times, but it's not smashing through unbroken parts of the rock, I think. And I'm curious what you all think about the ideas that you've been discussing and what can we learn from these cracks about past conditions, for example.
Jen, before we talk about the fracturing part of it, Jen Lamp, do you want to chime in about modern polygonal fractures that you observe in Antarctica? You turned your video on, so.
Yeah, sorry, I just moved to a different spot. So I haven't actually studied in detail the polygons that we see in Beacon and Mullins, which are like sublimation polygons that form over massive ice. So I don't know if I have too much to add in terms of bedrock fracturing and the relationship there. That actually was a plan when I was doing my PhD for someone to take a closer look at like the thermal stresses that massive ice undergoes and see if we can, do some sort of modeling. But we haven't actually done that much work there, except to have kind of a theoretical way that we think they form. That's by thermal contraction, and then sand gets in, you get sublimation through the sand, and then you kind of cause these fractures and the troughs between polygons to deepen, and that's how you form them over time. But it would be something that I think would be cool to look into, because I don't think anyone's done any real detailed modeling of that, or really examine the fractures beyond just kind of a theoretical model.
Yeah, if we believe Gerald Mack's model, then it's all from 3D tension, that form, that polygonal form that would go deep into the bedrock is got to be driven by tension. Monica, did you have your hand raised? Sorry.
Yeah, I think there's a large gap between an understanding of crack tip processes for an individual crack and what we actually observe on a landscape scale or, outcrop scale, which is a function of an individual crack growing and changing the stress field around it, but also the connection of multiple cracks. So we talked yesterday about crack curvature, which I guess you could think of as one crack curving through space or two cracks at different orientations joining. And on a very microscopic level, we assume that there's many, many planes of weakness that are around grain boundaries. And then those are preferentially propagated based on the stress field. But if we consider them separately, if we consider just a crack tip and then a macro scale, I think we're missing something really important, which is that the cracks themselves are interacting on a microscopic scale in the stress field. And in order to upscale that and understand the influence of the chemistry and the stress field and all the way up to landscape scale, there's a middle ground, which has to do with the dynamically interacting release of stress through the propagation of cracks. And I don't know if anyone is looking at how to model that. I've been thinking of it as sort of an energy balance, but I'd love to hear people's thoughts on that.
I think Jesse has his hand raised. Go ahead, Jesse.
Yeah, so I think to answer your question, Monica, and actually also to kind of follow up from what I've heard so far, is the kind of the pre-existing weaknesses in bedrock and the fractures that already exist kind of deflect the way that the later fractures join, for example, these fractures. So the fractures themselves modify the stress field within the rock, such that certain orientations are then favored relative to those fractures. So that's one reason why, for example, Doug's Jeromac's paper on cubic shapes is, especially when you have two opposing stress fields put upon each other, one after the other, there's this natural tendency of fractures to join each other 90 degrees to each other. So I do have a series of diagrams here that I'm not sure if I'm allowed to show those. Yeah, Jill says yes. I think I need permission to do that first.
I'm speaking for the group, so I can't.
That sounds good.
Try it again.
Oh yeah, there we go. There
Executive power.
So I hope you can kind of see. Let's zoom in on this one here. Do you see this diagram?
Yes.
Yep.
Excellent. So that's what I was talking about this deflection of fractures, and that's something you can see in rock examples as well. So something that I've done, not in a published form, but you can actually go and look at a series of fractures within rock and then derive the stress fields from those, and the order as well in which these stress fields have acted because of the reaction of fractures to pre-existing fractures. And then to kind of follow on from Monica's question, how do we look at this on a larger scale? So this is, for example, a folded series of sedimentary layers that experience both tension and compression, right? But then there's an added complexity because each lithology and the boundaries between the lithologies and their beds also form these pre-existing weaknesses, which then influence the fractures that occur. And for example, the difference in lithology also affects whether the rock deforms in a ductile manner or in a brittle manner, and that also then affects the way that fractures propagate. So I can keep talking, but I think the main point here is that there's a lot of knowledge from the geological realm here as well.
I have a question about that. And thank you for sharing that, because it relates to part of what Donovan was talking about and Jeff is, and this is for what happens to the stress field when you lose rock? You have rock fall, or you have plucking in a channel, or the glacial plucking problem. So you're showing this intact rock and the way the fractures are propagating, but what happens when you suddenly remove part of the rock, not all of it, not wholesale, not resetting everything.
Yeah, I mean, you're going to change everything. You're going to change the morphology of the existing fracture. So we have
and you change the stress.
and you're going to change the stress. Yeah. Phil, you had your hand raised. Did you want to follow up on that?
Well, yeah, I just wanted to come back. I think this is a really interesting discussion. And what I wanted to say in general was I think that you absolutely cannot separate your theme 1 about the morphology of fracture and your theme 2 about the stresses that drive the fracture. So as an example, I've got a question that I've been discussing with Ian Main, I think now for 30 years, and we still don't have an answer. So maybe somebody does. And I read so many papers and review so many papers when people talk about random fractures, and it does no good for my blood pressure at all, because I don't think anything at all is random. I think random is a lazy term for I don't understand it. And because if it's random, that's a very specific term, which means that things are totally unrelated. And I don't think that they are. So as an example, if okay, so I do most of my work in the laboratory, but if you take a rock sample, and it can be, from centimeters up to kilometers, I think, if you stress that mass of rock, because rock is a granular crystalline material, although we say, the stress is 50 megapascals, locally it's not. It's either 0 or 500 megapascals, right? Because so when you apply an overall stress to a rock mass, the local stresses vary considerably, and so it's not unreasonable to assume that the first crack that you generate will be in the highest stress zone. Okay, so you generate a crack. Well, what that crack does locally is it relieves that stress. So you suddenly turned the highest stress zone into the lowest stress zone. So your next crack, by definition, will be somewhere else. So that's not random, right? It's decided that it's got to be somewhere else because this is now a low stress zone. So it'll go to the next high stress zone. So you get this pattern of cracks all throughout your mass of rock, which looks random, but it's not. It's designed to be somewhere else. Okay, but once you get a certain crack density, enough cracks in there, then the cracks are close enough that the perturbed stress fields around those cracks see each other. And then suddenly they start to link up, because that's what they do. So if you've got, sorry, you can see my fingers. If you've got two cracks going like that, they will curve and do that and join together, okay? So suddenly, if that happens, those two cracks join, and now you've got a crack that's twice as long, and suddenly it sees more cracks. So it runs towards those cracks. So you completely flip from a negative feedback situation where a crack grows somewhere else to a positive feedback situation where everything concentrates on this most deleterious, largest flaw, and that grows. And that's exactly what you see around fault zones. You get this damage, and once the cracks start to interact to produce a fault, all the effort, all the stress goes onto that zone, and then you get a runaway failure. So you flip from negative to positive feedback. So it's not all about the individual fractures, but it's about the interactions. And of course, that's incredibly complicated to try to describe analytically or even to model. But that's the process we see. So you can't separate the very fact that you have a fracture there perturbs the stress that produced the fracture in the first place. So the feedbacks are the real key to all of this.
Yeah, and I think
throwing a bit of chemistry as well, and you go, "Wah."
And I think this is a nice transition now from sort of thinking about crack morphology into stress. And we can do that by going back to Dorothy's question to sort of transition she framed the question in a way that I think is very common in geomorphology studies, that the fractures, followed the bedrock or something like that. And I can't remember your words exactly, Dorothy, but, I think a lot of
Can you
us.
hear me, Tom?
Yes.
I'm in an AGU session for about another hour. Can I call you back after that?
Yeah, no problem. So I think, the way Dorothy framed the question, I think actually sort of puts in a misnomer in our minds in some ways, because, it goes to Silge's work as well. It's like, where's the interaction between, or where's the boundary? And I don't think there really is one. I think it's a very gradational transition between the stresses that are happening at the tectonic plate scale that induce a background noise of heterogeneities in the form of maybe smaller fractures, that then once the rock starts to experience other stresses because of what Phil just said, the fractures, the places where you have high fracture density are going to be the ones that are going to be the first to propagate into macro scale fractures that are observable, like in your landscapes, Dorothy. So in fact, I think it's, don't undersell, I don't think you do, but don't undersell the environmental processes that take advantage of the deep-seated structural heterogeneities that form in rock. Once you get within, Silge tells us 500 meters of the surface is so amazing. Her recent GRL paper, those rocks start to notice, if you will, the topography. She didn't like that terminology when I reviewed her paper, so I'd like her to help me to say it a better way, or how she visualizes it, but start to feel the stress that's related to the modern landscape. And I think that interaction, I think the vast majority of rocks, when we talk about joint sets and stuff, I don't think I propose to this group that those joint sets wouldn't be so evident without the added interaction from superficial processes, stresses arising for superficial processes. So I'll put that to the group. Maybe Silge can tell me, can lead us off there in thinking about how rocks, quote unquote, feel the surface. That's how I describe it, but she has a better way.
When you're saying superficial processes, do you mean superficial topography or superficial processes?
Everything. So topography, erosion over time, environment, climate, just that, the critical zone, essentially, just feeling all of the things going, all the systems that are actually happening at the interface between earth and air. So that's like topography, the landscape, that's erosion, that's climate. That's just how I'm conceptualizing it.
Thank you, Missy, to introducing our paper. It was great. You mentioned our paper, and in terms of models, what we include is the topography and the loadings and the sediment loadings and the pore pressures. But it was originally, when I first worked this one, I thought the abundances will be controlled by the stresses. So I compared the abundances, and there was no correlation almost. So the inherited rock fracture abundances was not clearly showing a very good connection with the stresses affected by the surface, or basically, the low stress from the surface. But when we do the relative abundances, like the percentages of the fracture, how many of them are open, it clearly shows the connection to the surface. So when but it's not just the depths, it is actually showing the differences depending on the stress magnitude, the maximum horizontal magnitude, and the this compressive stress magnitude as well. So we do see a better prediction compared to just depths, and that influence of the higher open fracture potential. And as Missy pointed out, it goes deeper to the 500 meter. But the paper itself, we didn't, right now I'm trying to extend this work, but we didn't include the past histories of the glacier processes. So we are using the present day stress measurement. People think that this strong compressive stress may have come from the differences of the loading or unloading of the glaciers. So we're trying to connect that whether when it's the happening of those high compressive stress and whether there's connections from the glacier. But it seems very evident that the 500-meter could have also influenced by the past glacier loading and unloading histories. Yeah.
Can I add to that?
Yeah, go ahead.
Most granitoid rocks that we see on the surface, they formed under compression, under compression at 10 kilometers depth. And then they effectively become a brittle rock and they're brought up to the surface. And they see this as a reduction in stress as they all the way to the surface. And so on this path, when we pick up a stone on the ground, it's effectively in tension from when it was formed. So they preserve as much of this tensile stress as they can within the bonds in the rock, but they lose it through generating fractures all the way to the surface. It increases as you get closer because the differential stress increases, but that's where we see most of our fractures forming from.
I would echo that. As I am looking over my computer screen, I'm seeing a mountaintop that's the closest to me, which is the Sandia Mountains. And the whole mountain front is formed by a coalescence of shear fractures that formed in the Laramide, which is 60 million years ago when they were under compression, and the present day Rio Grande Rift associated tensile stresses. And so you get a compromise between pre-existing cracks forming from the stress history, which is, around here kind of complex, but it's quite evident that they do control the present day topography in a lot of ways.
And to add a little bit, also coming back to Dorothy's comment, I think, rock type matters a lot. Of course, everybody agree here, and how they deal with those stresses and stress changes. Dorothy's mentioning, looking at fracture patterns in shales, which pervasively fractured and arrive at the surface pervasively fractured, and how they respond is going to be quite different than these massive granites that Carrie and Sugi and others have studied, and how they deal with near surface stresses.
Yeah, I was curious, Jeff, those arches are bedrock. Can you see evidence of the transition of those rocks feeling the stress, the sort of the large scale topographic and tectonic stresses versus a more morphologically connected stress of the arch itself? Can you see an evolution of that in different?
Yeah, there's definitely a hint of that. I mean, they're sandstones, they're more or less horizontally bedded. So, the kind of, rock mass structure is relatively clear. And then overprinted on that, we have all this weird salt tectonics out here, which folds things, faults things, and creates a lot of sort of weird, but relatively obvious fracture patterns. Then on top of that, we have this, maybe these morphological induced fractures. So we see this quite often where, in our arches, we get basically curving fractures that are following the lintel or following the curvature of the lintel, and cross-cutting bedding, cross-cutting any, cross bedding or whatever sedimentary structures. And thus are most likely, forming under the current stress field that is evolving in conjunction with the opening of the arch. And as compressive features, these are quite long and paralleling the underside of the opening, and quite interesting features to think about how they grow, where I don't really have a bunch of good answers here. You'll notice that I focused on the easy parts, which was the tension part. The compression part's a bit of a harder one.
Yeah, I'd like to add to Jeff's comment about the importance of rock types, and I'm going to share a diagram again. Sorry. So actually, the properties of the rock, the lithology itself, can determine whether a rock reacts to a particular stress field in a tensile or a compressive way as well. So the kind of the angle of the fractures and whether there's fractures at all, and the spacing of the fractures. I think you can see this here in a bunch of layered rocks. They have the same stress field, but they create different types of fractures and orientations. So that's just an add-on from what Jeff just said.
Can I
Okay.
go, Phil?
I want to comment. I'm really impressed, both Jeff's work and Carrie's work and also other people's experimental work. That was amazing to see the connections between the water, flow and then fractures, and you can definitely see the differences between the whole rock and the fracture induced water, and it was very interesting. And did you also try to fracture on the horizontal but the water flow in a different way to see that whether the fracture can grow differently? Or I'm not, these experimental works are so interesting, and the field measurement of those, sound, hearing the cracking sound with Missy's work, and they're all very interesting. And how is the different conditions, how can, is there any interesting things that you find that,
I guess that's for me. What I was going to say is that kind of to a comment of Monica's, I think a useful way to think about this is in terms of energy. So stress is essentially elastic energy that's stored in the rock, but there are many other types of energy that's available, and one of those is chemical potential energy, and the energy that's stored in the atomic structure. And so to answer your question, Sorgi, we make a number of experiments with at different moisture contents or humidity contents, and we also try adding water to dry rocks. And we find if we add water to a dry rock that is subcritically stressed, it will immediately start to fail, and it will fail in a few hours. And that's because of the chemical potential energy that's releasing the bonds, as Missy describes in her treatise on cracking or subcritical cracking. So we see the water affects it directly like that. But something else that we see in terms of fracture patterns, we try also compression tests, and when we raise the temperature in a chamber, humidity to 90%, we get condensation on the lower platen, and this condensation soaks into the sample and it soaks up the sample. And under compression, we have much higher loads, and we see that the sample fails at the bottom. It spalls off on the bottom after a few days. And so this moisture and the energy associated with that moisture is combining with the stress, and it's just driving this kind of subcritical cracking. It goes from being elastic to elastoplastic, I guess.
What a perfect transition to our next phase 3, our third topic. So the stresses, when you're talking about very slow crack growth, the stresses enable chemical reactions and chemical potential to be taken advantage of. I think that's what Carrie was just describing and seeing in his experimental work. Tom does a lot of this in shales, and maybe you could talk to us, Tom, about how another comment that came earlier was the difference in shales as they make it their way to the surface in terms of their crackiness is much different than, say, a granite. Can you speak to sort of, we're all, maybe not all of us, but some of us are familiar with kind of this more commonly invoked chemical process of stress corrosion, but maybe you can talk, what do we know right now about those crack tip chemical processes? Can we lump them all into stress corrosion, or do we all need to be thinking about a unique process for every rock we're trying to crack?
You're talking to me, Missy?
I am, yes. I'm putting you on the spot.
I think we've invented some new terminologies in this process of going through these sessions, and one of them is crackiness. I like that. as far as shales go, it depends on how you want to, you can look at it from a linear elastic fracture mechanics and talk about anisotropy and fracture toughness or something like that. But Peter Eichelbull were here. I don't think he's on this call, but all manner of difficulties with trying to come to grips with this experimentally, including about exactly where you wet and what you wet with and how water is deposed. And I was going to say, I'm getting off maybe what you asked me, but as I was looking at Carrie's presentation, I was reminded of a really cool study, and it was a fellow at University of Tennessee working at Oak Ridge National Laboratory. I was looking at wetting in rocks with a single fracture through it. It looked just like his diagram. And it occurred to me, I remembered this is something I was actually wanting to do last year and wrote a proposal which got denied. But in terms of a big question surrounds what's the disposition of water, and is it sorbed water? Is it wetting films? Is it and then it gets into disjoining pressure questions and things like that. So there's all sorts of two-phase flow terminology I could bring to bear to this, but the study I was talking about used neutron scattering, and you used deuterium or deuterated water. Maybe I just invented a word there, but deuterium water, heavy water, that absorbs neutrons differently, and you can track wetting fronts to submicron resolutions using neutron tomography. And it occurred to me that, wow, it'd be fantastic to do Carrie's experiments in a neutron beam and do this sort of neutron tomography, because it tells you exactly where the water is, how it advances, and its disposition, meaning how exactly it is wetting. And I think that's key to what you were asking, Missy, which is what is the disposition at the crack tip chemically and otherwise. There's been, I should have brought this up earlier, but I can't remember the folks who were doing this, but there was a session on molecular dynamic modeling, which is, again, a way of kind of saying what the disposition of the chemical species at a nascent crack tip is. And folks are doing fracture mechanics at the molecular scale, and they can say something about the exact disposition of the chemical species, the surface speciation, if you will. That's a chemistry term. It's not just water, but how the water is actually interacting with the particular chemical surfaces. And they get back to shale, that affects macroscopically we call an anisotropy and fracture toughness, because the characteristics of the clay minerals and so forth are different depending on how you intersect them with a grain boundary or with the fracture.
Yeah, I mean, it strikes me that, like, even in some place like Pennsylvania, where you have shales, that the pore water in shales is going to be perhaps more basic than in a granite, right? Maybe, and that in and of itself, and then we think about salts as playing this crucial role in desert environments, like in the Antarctica study that Matan had, and like what that's going to do for stresses, but it actually could be quite like Phil was talking about in feedbacks, like the chemistry of the rock itself, and then the pore waters that result from that, right? It create a potentially feedback mechanism for driving the fracture.
So this is one of the things I've been pondering a lot for ice segregation, where kind of the theoretical side of it is the stress is building at the crack tip. And you've got that undercooled water, that water that's below zero, stained liquid, that it's the mass flux of water that's being pulled from warm to cold that is creating the stresses of the crack tip and propagating cracks. And what I've been wondering is maybe we have it a little wrong, that it's also the chemical side of the water, this fresh water supply that keeps moving, getting sucked to the crack tip. And is it maybe the chemistry of that water, depending upon the rock type, and what it's doing to the bonds, that is contributing as much to frost-driven cracking as just this idea of the mass loading and the stresses at the crack tip. So is it a chemical, what do you call it? Chemical, physical, chemical physio? Let me mispronounce. Let me make a new word because I only mangle words. But is that as much of the process than just this, the idea we've had more of it just being the stresses, and we don't really think about the water itself and what it's doing at the bonds when we think about frost weathering. And that, you know, that might be a slightly different way to look at it, and that begins to get at some of the rock property, the mineral content of that rock, and how that might be driving some of the fracture propagation, essentially.
As you know, Phil said something about local stresses versus, you know, macro or meso, whatever you want to say, stress fields and stuff. But you can say the same thing about chemistry. You know, you can talk about the macro chemistry or the pH of water, but there's a local, it's a local chemistry that really matters. So, and that's difficult to kind of come to grips with. You know, you with all the hydrofracturing and sort of living in the oil and gas world here, you'll see trucks go by with huge tanks of hydrochloric acid and they'll pump it down. Talk about a brute force fracturing method, you know, and they do it because in some fields, someone had the idea of doing it and it worked. And you got a better connectivity through your rock from a hydrofracture process. So chemistry matters, I guess.
Can I comment on that?
Yeah, go ahead.
I think I completely agree with what Tom just said, and I think even if you don't artificially dump stuff down into your fracture, the chemistry of the fluid is dynamic anyway. And I remember reading a paper some time ago by Ojala and Main, and they were able to sample pore fluids, and what they found was that when fractures were growing through their lab samples, as soon as a crack starts to grow, it exposes new fracture surface. Mostly it was, I think it was in a sandstone, so it was mostly quartz. And though that new fracture surface is very, very electrochemically active, and so you get solution into the pore fluid. So the chemistry of the pore fluid is changing, you know, and they were able to measure how many parts per million, I had no idea, of dissolved quartz. So we always use water in our experiments because, like, we have water, but it's not going to be water, and the chemistry is changing dynamically as rocks are deforming and cracks are growing. So that change is something that's almost been ignored because probably it's too complicated because about it, you know. So I think there are many factors to take into account to try to understand this stuff. And going back to this point about shales, some stuff we've been looking at recently, we've been looking at fracture through shales, and the shell we obtained was from a bedded sequence of limestones and shales. And when you actually go to the field, you see, okay, so the shale has a significantly lower fracture toughness than the limestone. But when you look in the field, there's lots more cracks in the limestone than in the shale. And if you actually calculate the fracture energy of the shale is much higher than the limestone because it's less brittle. And this is important. And this got me excited in a conversation with a colleague who was a volcanologist. You know, what's he care about shales and limestones for? And it's because in a stratovolcano, you've got these layers of lava flows and pyroclastic flows. So you've got more brittle and more ductile or high and low elastic modulus layers. And so if you're trying to propagate a dike to the surface, it's got to go across all these layers. And what you see sometimes, the fracture goes straight through. Sometimes it gets to an interface and it stops dead because of the difference in mechanical properties. And sometimes it opens up that interface, so you get a vertical dike growing up, and then you get the sill because the layers separate. So, you know, that's an extra complication of going through layered sequences. If they've got different properties, does the fracture propagate? Does it stop? Does it deviate? Sometimes it can do any of those things, and it does. And the other thing I thought that was interesting relative to this stuff about topography and near surface stresses is that if you look, for example, it hydrofracturing in shale sequences, you've got a combination of anisotropies, because the shale is easy to propagate fractures parallel to the bedding in shales, if bedding's the right word, you know, to the laminations, and it's difficult to grow fractures across it. But as you go down in depth in the earth, the vertical stress increases generally faster than the horizontal stress. So what you find is if you hydraulically fracture in a shallow borehole, you'll get a horizontal fracture. And if it's a deep borehole, you'll get a vertical fracture, because there's a crossover point where the anisotropy of the crustal stress overwhelms the anisotropy of the strength of the material. And I think, and there's a really good diagram in a paper by, I think his name is Warpinski.
Yeah, Norm Warpinski.
Yeah, and the guy put together data of orientations of hydrofractures in boreholes in North America, and there's like about 2,000 data points in this plot, and basically the curve looks like that. So in shallow you get horizontal fractures, and when you go below about 800 meters, all the fractures are vertical. So it completely flips. So, you know, and I guess that depth would vary depending on the overlying overburden stress. So it would matter whether you're in a valley or below a mountain, and so topography would come into it. So there's a lot of complexity in all that stuff.
Yeah, that sounds like a study that some geomorphologists could take advantage of.
Yeah.
Okay, it's almost 11, so I want to switch to our last sort of overarching or underarching theme of across all three of these topics, which is time. And I think Phil out loud and Monica in the chat brought up the connection between chemistry and time, and that as water sits in a crack and its chemistry changes, so will the fracture processes change with that, depending on whether the fracture is propagating, exposing new material. But I think Monica's work, Max's work, Jeff's work, all of these are observations that are using sort of space for time to tell us how processes are changing over time. And I'm not sure that there's any other way to do it in a geomorphic setting, or actually that's one of the unique ways that geomorphologists are what we're used to doing space for time studies, sort of chronosequences of weathering, if you will, and thinking about stability versus instability and how that translates to an accumulation of damage or fracturing. So thinking about how the morphology of cracks changes over time, how stresses change over time, and how climates change over time, I think is a really interesting way to validate sort of short-term experimental data using this field of geomorphology, using long-term observations of different exposure ages. Go ahead, Jill.
Can I add, I think there's 2 N members that have come out of this session or sessions. One is rocks that sit there. The Antarctica rocks, you know, the Tiras rocks, versus rocks that are perhaps where you have rock being removed, for example, you know, on the mountain faces or in rivers. And you know, the river. So we kind of have these 2 N members of things that just sit there and accumulate. It changes through time. And then we have things that are kind of dynamically, I don't know if what the right word is, not rheology, but those are kind of our two end members for thinking about this. Is that appropriate?
Maybe so. Although, I mean, I think that, you can use like rocks that physically sit like on a surface, like on a surface of a glacier or of an alluvial fan as a I think I don't think you have to separate those fracturing processes from processes that happen in bedrock, say, that's being eroded at different rates. So like Jeff's work in stream channels is a perfect example of that. So he has the channel bottom that's being eroded at a much faster rate than the channel margins. And so I'd say, that's sort of a dynamic version or a bedrock version. That's a dynamic version of the same thing that Monica and Max are saying versus from a recently deposited rock that's only 1,000 years old versus one that was deposited 10,000 years ago. So I think I don't know that you need to separate them personally, but
I think there might be a little more resetting in some of the where you have the active landscapes. And so you have, you might have a constant change essentially in the conditions as opposed to a reaction to what was before. I don't know, but that's for the discussion. That's,
Does anyone want to pipe up? So I, of course,
sorry, I do want to. I have a slightly different take on this, which, and I'm looking at your point 4 here on rates and time, and I think a key thing is to look at is scaling, both in time and in size and space. One of the issues that I've spent many years counteracting is you give a talk about something you do in the lab, and some field geologist said, yeah, but how does what you do on a 5 centimeter sample in a day tell me anything about my volcano over 1,000 years or 1,000,000 years? And it's completely irrelevant. And I could say, well, no, I don't think it is actually, because it's about understanding process and but it is a key element, and it's a criticism that gets raised time and time and time and time again. How can you understand anything about large scale and long term from small scale and short term? And the point I try to make about things is you're not trying to entirely replicate what happens, where you're trying to understand processes and then say, well, okay, is it possible for this to happen? And it may be, and it may not be. And so, I think a lot of people in geology try to get you to totally replicate what they see in the field. And you say, well, no, we can't do that. Well, what we can do is look at the potential processes that might be able to happen under those circumstances, and that will get you some understanding about what's possible and what's not. So you kind of got to rejig the question to the one you're able to answer.
That's funny.
That's a key point. I think that's a key point, Phil. And I do think that there are a lot of us field geologists who do a lot of hand waving and conceptual models, and that being able to test that model, that conceptual model in the lab, we're trying to string everything together, but testing whether that process can actually do what we think it's doing is key. I'm a big admirer of the experimentalists in the group.
Yeah, and it's funny because if you get those questions every time I present like the conceptual framework of subcritical cracking and its environmental dependence, they're like, well, you should do experiments to show that. And I'm like, I don't need to, because people have been doing experiments for 30 years.
Well, exactly. And I think the point is that we're all trying to get to the same place, and we're all limited in what we can do in getting there. And you've got to put all this stuff together. And I think that's the key point in all of this. Yeah. Anyway,
Yeah.
For me,
Go
when I
ahead,
think
Donovan.
about this, one challenge is it's kind of like what's the critical moment, I guess, is like when do we reach the point? I think of that everything from the perspective of erosion and excavation. And so when does the crack formation and when does the crack tip breaking to the surface, or however it does, lead to a failure and lead to excavation if it's a rock fall, or and I think, Jill, maybe you were trying to kind of hinting at that too with your, does the rock sit there or is the rock coming off? And so, I mean, that's the biggest difficulty for me, is to think about it as the summation of the processes and what are the relative importances of certain processes, and comparing across the different types of cracking. And, you know, for example, in calcareous rocks in the northern European Alps, perhaps chemical weathering is in fact much more important for crack formation than where we are sitting in the granitic Alps. And how do they interplay? That's my biggest challenge in leading to the critical moment of erosion or of just failure.
I think for me, one of the things I get hung up on is antecedent conditions and how long, like, you know, I tend to think in a glacial interglacial cycle scale and switching back and forth in between soil production and erosion processes, for example. And so, you know, how long do conditions of the past continue to, I mean, you have the influence of just the architecture, but I don't mean that. I mean more like how long, you know, we tend to say that things change and now everything's different. And we need to think about it, we segregate it, we layer cake it. But surely there is synergistic propagation of either negative or positive feedbacks that are dependent upon antecedent conditions from past climates, for example, past processes. And how long do we think about those propagating is, you know, I think one place I'd love to collaborate with experimentalists to have a little more understanding of that.
You know, something we tried for our master thesis was modeling a block on an inclined slope with a crack at the back. And we grew the crack with Paris law and Charles law. And we looked at how the crack propagated. And we tried all different sites of geometry, whatever. And Paris law is dependent on cyclic stresses, and Charles law is dependent on essentially the stress intensity factor, which is dependent on the crack length. And for all of the geometries and all the models, Paris law got it started, but Charles law led it to failure. So I think for Donovan's question, it starts to go when the cracks are long already. So it's when Charles law, which is dependent on the chemistry and dependent on the energy, when that takes over, that's the point that things are getting ready to go.
I think some of this is seen in some recent work that Missy published just a couple of weeks ago, where essentially the cyclical stresses sort of prime a rock for breaking, and then at these moments where you have, you know, large changes in temperature or a big increase in vapor pressure, that's sort of at the correct time of the day is when you get a huge influx of cracking events. And I think that's sort of the practical example of what you're talking about. And this is based on a couple of years of data, but in the natural environment. So I think it's very clearly seen in the real world where you have these sort of extreme events. And the presentation by Joan Marie Del Vecchio during the AGU and a presentation she did a couple months ago, you also see this with long-term climate change, where you have the end of a glacial cycle, and that leads to this massive influx of erosion, and you see that pulse for a very long time. So I think that once we get up in our data, once you get up to say 50,000 years, everything kind of gets integrated, and you say the erosion rate kind of stabilizes. But anything in the past 50,000 years is going to be subject to these sort of stochastic processes that are really the big impactful events.
Yeah, one way to think of that, Brian Collins and Greg Stock have really nice work that show this for exfoliation domes and rockfall, where particularly this critical, what you're talking about, Donovan, like the critical exfoliation event that was captured on video, when you do the back calculations for the stresses that are necessary for that, it's just what Carrie said. You can't get enough ambient stress, even if you combine Solge's tectonic stresses and the thermal stresses Monica was just talking about. You can't get enough stress unless you have a long enough crack. So even though the final stage of crack growth might need a big push in terms of an extreme event of some type or another to add enough stress, in fact, even that stress wouldn't have been enough if you hadn't had tens of thousands of years of slow, steady crack growth to get your crack long enough to begin with. So it's this fascinating combination of sort of threshold exceedance plus the entire stress history that Jill was talking about, maybe where that's happened over, many different cycles of climatic influences or even erosional influences over time that allowed the cracks to get to the point where just the regular stresses, the peaks and the regular stresses, the cycles of stresses that naturally occur could actually tip us over the end.
I do think it's important, though, to differentiate in between, and Monica, this gets to a little bit of your point about Jo Marie's work, is there is a difference in between when can you break the rock, when can it fragment such that it's available to be mobile versus other things that might make it move away. So there's a transport side when you're on hill slopes, for example, of setting up the conditions to actually move the material, which is separate from the do you have long enough cracks and do the cracks coalesce such that you go to from an immobile material to a mobile material.
So before we comment on that, it's a lot. I want to take an opportunity to, like, if we were on the radio, we'd have to say, this is WCRACK, and we're coming to you live from AGU. So to just give everyone a chance if they need to go to say, I just want to pause and say thank you. But I'm happy to continue on the conversation. But if people have to go, just say goodbye in the chat, and we won't think any less of you for not staying on for 2 or 3 hours of crack talk. So
I should also add that if anyone wants transcripts of the recording or the chat, just email Missy or any of the conveners, and
yeah,
we'll
we can make these available. Okay, so so we can continue on, with what we were just talking about, which is like how we in geomorphology we have to be cognizant of the fact that we need rock fracture, but then there's a whole suite of other processes that and this goes back to Donovan's question, is like to change bedrock into something mobile. Fractures, the ultimate thing is that fractures have to coalesce, because you literally need a piece that can move. So that to me is the fundamental idea that that coalescence of fractures, interestingly, is different for different rock types. And again, this goes back to Jeff's work and then some work that I've done in Shenandoah that shows that some rocks, because the coalescence is happening, or the meeting of the fractures is happening so slowly that in some rocks like quartzite, like think of vein quartz, of how cracky vein quartz is, but how strong it is. Those cracks can actually get quite close to each other, but still not break off. I mean, try to break up, think of how cracky vein quartz is and try to do this with it. You can't. But if you had the same amount of crackiness in a shale, you could. So, and that relates to the ability of those cracks to continue to coalesce and join. And I think that's really a fascinating aspect of this, is that, we think as geomorphologists, we've often looked at the fracture spacing, fracture density as a proxy for erodibility, and it is within a single rock type. But once you start crossing rock types, because of the crack tip processes and their susceptibility to chemistry and environment and all of that, fracture density per se is not necessarily a proxy for erodibility. I think
So
that
I'm curious, because that gets to kind of what Phil was talking about yesterday in the discussion, or maybe I'm totally off on this, but the idea that you can have a small crack and a big crack, and they don't necessarily feel one other stress field. But once the cracks are big enough that they feel one of the stress fields, so the stress there is only one of them is going to grow. So does that mean that am I interpreting that right, Phil, or repeating it correctly?
Yeah,
more or
yeah,
less?
yeah.
So does that mean that in quartzite that you don't have it takes longer for the cracks, or it takes less time for the cracks to feel one of their stress field?
it's not so much that they're not feeling the stress field as that the stresses required to propagate are higher.
Yeah, they'll see it because that's
Okay, good.
just,
I was puzzled by that. Okay.
it's just a geometrical constraint. If once the crack length is equal to the crack spacing, then the perturbed stress fields overlap, and therefore the crack A knows that crack B is there, essentially, and therefore they tend to coalesce, or one grows at the expense of the other. They can't both grow if they're parallel cracks. Obviously, if they're coming in opposite directions, when they see each other, they grow towards each other. And then, of course, this is why you get this runaway failure, because if you think you've got two cracks of length 1, if they grow together, then suddenly the crack is of length 2, and then it sees many more cracks, because it then sees cracks at a distance 2 away rather than 1 away. And so suddenly it becomes a positive feedback process. That the longer a crack gets, the more it sees other cracks or perturbed stress fields. So the more coalescence. So the coalescence accelerates, and that's why you go from this negative feedback to positive feedback.
But the speed of the coalescence is really
Crack
dependent
morphology.
on the material properties.
Yeah, to
But
sort of
obviously
bring
the
it
stress
back
is
to
required for
the
that.
to bring it back to the energy discussion that we were having, I think it helped me a lot to think about fracture toughness as a material property, and that property is the ability to absorb that energy. So something like a quartzite can absorb a lot of the energy regardless of it might have the same geometry as a weaker material, and they might be feeling the same amount of energy, but it can absorb a lot of that energy sort of into the media before the fracture propagates.
Yeah.
So that's a way that it sort of made more sense to me.
Yeah, and I'd like to add to that point from Missy as well, that there's on the one hand you have things like fractures, so structural controls on erodibility, and on the other hand you have lithological controls, inherent strength of the rock. And so one way in which I have looked at this is if you go in the field, for example, you can take in situ measurements of the inherent strength of intact rock, for example, in outcrops and stuff. But then at the same time, observe that in all of these lithologies, there are structural weaknesses and fractures. And to kind of judge which one is more important, I then compared the measurements of or the predictions of erodibility based on the strength with what we actually see in the geomorphology. So in this case, compared to normalized river channel steepness. And what I found from a theoretical point of view, the lithology accounts for, actually surprisingly accounts for most of the erodibility differences between the rock types. But there is definitely, so say, actually I'll show you this figure here. So if you just concentrate on the top two here, oops, I just okay, that's my fault. I just oh, there we go. Oh no, yeah. So if you look at these here, from 0.1 to 1, that's from the rock strength alone. So it's the weakest bedrock here, strongest bedrock here. But then, and if you look at the kind of the geomorphology, and we take the NS2 line here, you see that the magnitude of difference in erodibility is less, and that's because of the structural controls. But it's still, the lithology still seems to have a significant, more significant impact on the landscape in this case than structural controls, although the controls are almost equal.
So interesting. So, okay, so I think we've made it through. That sort of takes us back around to sort of thinking about crack morphology again and things like that with this time. One thing I don't think we have talked about too much is how to link. Well, we talked about this runaway, this runaway idea that as cracks grow, they concentrate stresses and can then continue to accelerate. But and then there's the opposite idea that also as they grow, as a rock body accumulates cracks, that the total accumulation rate of cracks will decrease even as perhaps one crack is accelerating. And this is changing with this changing stress field. And I think that is what both Monica and Max are seeing in their field data, where there's an initial acceleration or very fast rates of crack growth, followed by very little change at all over long time scales. You guys want to talk about that? I'm just making a plug for my own students and postdoc, just shamelessly now.
Can I ask a question related to that? What is the largest grain size you're looking at?
In my data, it's maybe 4 or 5 millimeters max. A lot of it is this sort of coarse grain, 2 to 3 millimeter grain size granite, relatively isotropic. At least from what we can see.
I mean, I'm just, in my scale up world, I'm thinking about, you've got this individual thing with your cracks that are doing fills positive to negative feedback. But, translating that to, so I'm curious what the largest size rock people are looking at, because 4 to 5 millimeters is pretty small. Do you mean centimeters or millimeters?
No, I mean the grain size is 4 to 5 millimeters.
But what's the biggest rock?
Oh, yeah, wow. The boulder size for the transect data that I presented was between 15 and 50 centimeters. So, hand size. And we also collected some data from beryllium boulders. So those are meter scale boulders that the dates came from. But we collected crack data on essentially squares, sections of the boulder. So we didn't measure the entire rock, but that was not included in the data that I presented. So we're essentially removing the scale of boulders is such that you would assume that thermal stresses basically propagate through the entire body throughout the day. So it's not necessarily scalable to bedrock scale, but I know other people have done work on that, like the Collins papers about, and basically what Donovan is working on as well. So the bedrock stress, I think it's a similar sort of mechanism and rate, but the tectonic stresses add a whole other complication that I'm trying not to look at right now. But it is quite interesting that we saw a lot of a different, sort of preliminary analysis looks like the grain boundary cracks that essentially form growth. So what's going to control the erosion rate measurements, supplying small sediment to the landscape, appears to behave differently than the whole rock stresses. So like a through-going crack or exfoliation cracks on the outside of the body. And I'm really trying to tease out what is going on there and figure out, you know, whether they peak at different times for reasons that we can explain, or if it's just difficulties in being able to only look at the outside of the rock. Because as we also have seen that like large cracks that propagate throughout the entire body based on simulation don't form from the outside in, they form from the inside out. So we won't see them until they've cracked the rock open, but they may be acting in abundance early in the life of the rock and we're just not seeing it until it's cracked open.
Right, right. I mean, my experience digging pits in a lot of granite landscapes is that for gross landscapes, basically at that point you're at the mineral scale size. So you have like you go from the cracks not connecting to suddenly everything connecting, and you just going to gross. So you actually get a bimodal distribution oftentimes in granitic landscapes. And I've often, yeah, so I think I always think of granite as the weird one, partly because of biotite and other things. Like it behaves in a singular way in pit when I've looked at, you know, digging down into saprolite compared to any other lithology that I've looked at. I just think granite's weird. I don't know why everyone studies it.
I have a quick question. Do you guys in the field rock, did you do any of the synchrotron X-ray microprobes to see whether those fractures are occurring? Like the biotite is actually opening in terms of mineral levels, to see whether those decreased rate over time is because the fractures are all healed or they don't have some different behaviors in terms of, you know, weathering of mineral. I don't know, Carrie, you're in the experiments too. Do you also see some kind of like the thin sections or like weathering features on the rock itself?
I mean, of course, we see the fracture eventually when the beam fails. And with my past student in Voigtlander, we looked with an SEM at the fracture morphology. And we think we can see like morphological differences where the crack is subcritical and critical.
Oh, that's cool.
But it's super hard to quantify. It's just like us looking at it going, yeah, I think that looks like that. And it looks so, I don't know, maybe she had a good day or a bad day.
Is it smoother when it's critical and rougher when it's subcritical? That would be my intuition.
Yeah, when it's subcritical, it tends to follow grain boundaries, like Phil said. So we see less kind of ruptured grains. We still see some like signs of critical fracturing, but not so much. We made porosity measurements on our samples. We have a fine grained granite, and we made thin sections of it, and we can see like a few micro cracks in the thin sections, but it wasn't really what we expected. And it's quite isotropic in terms of the elastic wave velocities. But we looked at the crack sizes using nitrogen porosimetry. And from this, you can get the surface area from the cracks and as well as the size or the volume. And 80% of our crack surface area is less than 10 nanometers. So to put that in context, like a water molecule is 0.3 of a nanometer. So even though we can't see the cracks, these very, very small features make up most of the surface area. And it's the surface area for us that the water is reacting with. So even though you don't necessarily see it, it doesn't mean that it's not playing a part in the way that the rock responds. And I don't know, like Jill said, granite's a bit funny, and we took like a rock from a quarry, which is even stranger. And I'm not sure what it's like, for example, for Jeff with a sandstone. I don't know what these look like in terms of pore sizes.
Yeah,
we've been running stuff here through the micro CT scanner to try and get with a lot of runs to get really, really high resolution to try and get at fracture spacing and void space. So if people are interested, the micro CT scanner here is often just sitting around, and it doesn't cost that much to run samples on it.
People have done work using surface profilometers to look at the roughness of surfaces and try to relate that to the crack velocity. In the labs where you know the velocity, so you can kind of interpret field scale fracture roughnesses. People have also looked at how many grains what proportion of the grains were subject to intergranular cracking rather than transgranular cracking, and it's extremely tedious and boring work. It's like watching paint dry, but that's quite important, I think, at that scale. But I think there's another scale there that, of course, even if you can understand the fracture properties of quartz and feldspar and mica, that isn't going to tell you anything about the fracture properties of granite, because when you look at the ensemble, it's got completely different properties. And I think the reason rocks are strong in compression is because the fracturing is so damn inefficient. Because if you actually look at the fracture process, you've got a main fracture that grows, but you've got lots of hundreds and hundreds of little branch fractures which don't go anywhere, but they all absorb energy, and that's why the rock is strong, because of all the wasted energy. So I think you've got to have a crack length that spans a multiple number of grains before it's representative of the rock material rather than just the individual minerals. And we also found that some work I did with Ian Main and a student many years ago, we looked at fractures, tensile fractures, tensile fissures in Iceland, and we found that the actual growth process didn't become representative, although this was in granite, which is extremely fine grained, it didn't become representative of the whole mass until fractures were at least 3-4 meters long. And that was because as the rock, this is lava flow material, as the rock had cooled, it had broken up into columnar joints, and the columnar joints were like 20 to 30 centimeters across. So that imposed a different kind of grain scale. So the fracture through the mass only became representative of the mass, and it got a uniform value above like 10 or 15 times that grain size. So it had to be like 3 or 4 meters before there was a uniform growth law. So there's various levels of complexity in that process as well.
Okay, maybe we're losing steam finally after 2.5 hours of crack talk starting this morning.
Well, the same thing Phil said about columnar joining. It's mostly true for beds too. Anisotropy notwithstanding.
Yeah.
To get a full rock package, the shale is a bunch of little lamina, and to get something that's a representative elementary volume,
exactly,
or however you want to say it, it's different scales. You're talking about cracks this big, cracks this big, cracks that big. So.
Yeah. I think that's right. And so what's true at one scale isn't true at another scale. Yeah.
Yeah, and then once you add sort of environmental stresses in it, different processes are going to be more efficacious at different scales. So going back to sort of this idea that granites act differently, the grain scale thermal stresses in granites are just so much bigger because it's the stress intensity of two adjacent minerals that are pretty big. The crystals are pretty big, and so the size of that mineral matters for the length of the average flaw along the grain boundary. So the boundary between a big quartz crystal and a big feldspar crystal and a granite it's going to provide a source of heterogeneity of stress concentration right there. And then quartz, has this big coefficient of thermal expansion that, when you butt it up against a felspar, is really going to put stress right on that already sort of big flaw, which is the grain boundary. So there's that, that's an example of like how granite really takes that stress as opposed to sort of the regional stress in bedrock of granite and how it responds to that, and fractures that may take off or grow in response to much bigger sort of what Carrie was talking about quite a while ago now in the conversation, like exhumation stresses or tectonic or topographic stresses. So, and then that, so to say, to really say all cracks are from one thing or even one combination of things, I think is a way oversimplification. It's probably that the family of cracks that we see is from different parents. It's a complex family of fractures probably that in any given rock outcrop that makes it to the surface.
So can I ask you a question? What was the feedback you got from SKB from your work? What was the most important thing or the most interesting thing that they found from your work?
I think they were like, so originally the impression was like, what? There's a fracture opening on the 500 meter, but the abundances are very low at 5 meter, 100 meter depth. The abundance of the fracture is actually quite low, like 3 or 4 per meter. But what is opening is the one that connected to subhorizontal, slightly oriented to in between the most compressive and most in between that sigma 1 and 2. I think I did show what fracture is slightly more open compared to the other. So I think that they liked that one, and so that's getting the data was hard in the beginning, but once we got the data and then show that there is some connections between surface and maybe the whole stress field is important to determining which fracture may open. So I think that was a very positive feedback from SKB. So I'm interested in if you have some other people who has data, at deep boreholes data like that, I will be happy to collaborate, because it was rare opportunity. Like in terms of, we don't have many boreholes with kilometer depth. And also because they worried a lot, they actually have those observations, which fracture is open. So they have all these documentations of these fractures actually have open and have apertures and the minerals. Another thing that for the future work that we're trying to do is there is a lot of secondary minerals on those fractures. And depending on what minerals in the secondary minerals, it seems that the proportion of opening of the fracture changes. That's related to Missy's point that, whatever that inherited rock fracture with what is filled with calcite or some other minerals, like minerals with a lot of sheets, that seems like they are also contributing to the reactivation of those fractures. So, yeah.
Before someone comments on that, can y'all just tell us who the they is? Tell the folks that aren't familiar with the work, like who you're talking about, because I think it's really interesting intersection of industry with academia.
Oh, yes. See, SKB is a Swedish nuclear waste companies. So they have to investigate all deep bedrock fractures because they want to have a future repository for the nuclear waste. So they had 3 different sites that they initially investigated, and this Forsmark that I studied is the final repository candidate. So they have 20 boreholes, and 10 of them goes to kilometer depth, and they have all the fracture images and cores and observation data too, like minerals and openness and apertures and all this data. So in the industry, seems like they do have a lot of deep fracture informations, but having those contacts to the industry people was you need to reach out. But actually, my office mate, previous postdoc in George's group, actually went to Sweden, and he had a connection, so he contacted me to work on this project. So it was through the personal connections. But I hope these studies that we do can advertise to the industry that can have some fundings and have some data, so we can contribute to science as well. Yeah.
Yeah, I think there's a lot of fracture data out in industry. Go ahead, Monica. She worked in the oil industry for Houston.
Yeah, I was just thinking that a lot of image log analysis is probably much deeper than what you're looking at traditionally, but you may want to look at some of the fairly recent fields in places like the Marcellus Shale. There's some oil and gas fields that are sort of shockingly shallow, and they are in a lot of these highly folded areas. So there may be some data available for image log analysis in like the Marcellus in Pennsylvania, and looking at where they usually only take the image logs over a very limited zone of interest. But there are definitely large databases of image logs out there. Usually they're not free, but I know that sometimes universities can get access to them. I was able to access a bunch of data when I was in Australia through some coal mining projects, because they also have coal that comes up fairly shallow, and that has its own, properties of coal fracture. But in terms of looking at the structural controls of the surface, I would look into shallow oil and gas and coal fields. And of course, things like you're looking at nuclear waste disposal and enhanced geothermal systems are at a lot of different depths that may be influenced by the surface topography.
Carbon sequestration as well. And there's, consortiums around the world that have a lot of nice fresh boreholes that are they just characterize the heck out of them. So similar.
Thomas, I heard from just like as hearsay that when we have these like beautiful kind of slate plates for our table, and I heard that when they split the slate, they have to split it when it's fresh and when it's wet out of the ground. I don't know what you do, but do you have any idea why, if that's true?
Don't know.
It's still hearsay.
Might be just a remnant residual stress, from them being recently quarried or something.
Yeah, I was told
there's
like
a time to relaxation.
I was told if they relax, then there's too many microcracks forming, and they don't split nicely on the planes anymore. But I'm not sure if it was just a.
Yeah, there's a lot of time dependence. I remember working on the Amoco building in Chicago, where they would quarry Carrara marble in a mountaintop in Italy, and drive it down to a boat that would ship it across the Atlantic and across the train to Chicago, and then they put it on these nice marble panels, and they put it on this building in the Chicago winters, and it would just slowly deform, and they had to replace the whole side of the building because the marble was going to come down on people's heads and stuff. But it was all, some of the marble would basically not explode, but just on the truck ride down the mountaintop, the sides of the mountain were littered with the blocks of marble that had basically blown up, if I can say that. Didn't survive the truckload. Some marble didn't survive the train ride across the eastern U.S., and some marble withstood it. And it all had to do with if it was quarried from the nose of a fold or whatnot, all manner of factors. But there's enormous time dependence.
Very cool. Okay, I think that we probably ought to wrap up just because we. As I said, people are trickling off, but I want to put in a few plugs for future conversations along these lines. Silke is hosting a session at EGU called Stressed Landscapes or something along those lines. So if you're attending EGU, consider participating in her session are submitting an abstract, which I believe they're due January 13th. Do you want to say anything about that, Solgi?
Yeah, thank you for commenting that one. Yes, we have with Anne, which is Carrie's students, and some other people hosting the convening virtual EGU. So even though we are in North America, we can still participate in like AGU. So I encourage you look at our session and submitting the abstract. It's great to learn from convening this session from Jill and Missy. So we can try to do that again in EGU session, so I can have a lot of conversation. I learned a lot, so it was really good to talk to you, everyone. Yeah.
Thanks. And then also today, Phil and Carrie and Carrie and myself and Matt Brain and Alex Reinhardt at New Mexico Tech are submitting a proposal for a progressive rock failure conference, similar to one Carrie hosted at ETH in 2017. And Phil and Jill, I think, are on our international advisory board, and we're submitting that to GSA for our Penrose conference today. So the deadline's today for that submission. So wish us luck with that, and hopefully it'll go through, and we'll have a week of conversations like this in the summer of 2022. So knock on wood and mark your calendar for that. And then I think we will try to continue on with a session like this in future years at AGU, and try to stay in touch with one another. So thank you to everyone. It's really just been so fun to do this, and I feel like it's just the beginning of a long conversation about fractures and landscapes.
Could I add a little anecdote before we sign off?
Of course.
Just to say, I mean, it's an absolutely fascinating topic which has kept me busy and gainfully employed for about 40 years. When I started my PhD looking at fracture mechanics in rock, there weren't a lot of people doing that at the time, and there weren't a lot of publications. And so the conference and journal of choice I had to turn to was the Journal of the American Ceramic Society. And when I went to one of their conferences over conversations after a real physical session, these guys looked at me and said, "We're trying to study fracturing, how cracks grow through our perfect cubic ceramics, and we don't understand it. You guys are looking at these rocks that are all messed up and full of crap. You stand no chance." Unfortunately, I think they were probably right, but I said, unfortunately, the world is not made of cubic ceramics. It's made of these horrible, messy rocks, and so we have to do the best we can. So here we are, 40 years later, still imperfectly trying to do the best we can. So good luck to everybody with that.
Thanks, Philip, for not solving all the problems before we go.
or indeed any of them.
Well, I think that's a perfect note to end on. We have our work cut out for us. Well,
Absolutely.
we think bringing you rock physicists into the world of surface processes is going to help us all.
I think the point of the anecdote is you're not going to run out of problems to solve in your lifetime. That's for sure.
Amen to that.
Anyway, thanks for organizing all this, Missy, and doing that. It was really good.
Yep.
Yeah. All right. Well, thank you, everyone. Happy holidays and Happy New Year.
Yeah.
And we hope to see you again soon.
Have a good time, and hope to see you in reality at some point in the future.
Yes.
Hopefully.
Yeah.
Bye-bye now.
Bye, everyone.